Welcome, everybody. I want to talk about the Atlantic overturning circulation, and in the general public, that is sometimes known as the Gulf Stream system. The Gulf Stream itself, actually, if you look at the diagram here, is only the red surface current that goes along the coast of the United States and then into the middle of the Atlantic. But the Atlantic overturning circulation is a much bigger system, as you can see. With it actually also comes from the South Atlantic, flowing through the Benguela current of the South African coast, and then crosses over through the Caribbean, the Gulf of Mexico, then into the Gulf Stream, and then actually in the middle of the Atlantic, it has this bifurcation where part of it recirculates on the eastern side of the Atlantic near the surface. That circulation is the wind-driven subtropical gyre, and the other part continues up further north. It's called the North Atlantic current, and it goes even between Iceland and Scotland into the Nordic seas. In these high latitude areas in the Labrador Sea, Nordic seas, and in the Erminger Sea, that water actually sinks down to depth, and it then flows south as a deep current between 2,000 and 3,000 meters depth, shown in blue here, as a deep western boundary current out into the South Atlantic again, and eventually into the Southern Ocean. So the Gulf Stream proper here is made up of two parts. It's to a larger part, it's part of that subtropical gyre, simply a surface circulation, and to a smaller part, it is part of that upper branch of the Atlantic overturning circulation. The latter is actually driven by density differences in the ocean waters. The high densities in the cold northern areas makes the water sink down to depth, and that's why it's a thermally driven overturning circulation. And it has a big effect on climate. The whole northern hemisphere is warmer because of that overturning circulation, because you can see here down there it crosses the equator. There's a warm surface current flowing north, a cold deep current flowing south. So there's a big heat transport northward across the equator. Even in the South Atlantic, there's a northward heat transport. And that means that this is quite anomalous. The heat transport is towards the equator in this case. And that heat transport goes through the entire North Atlantic, the South Atlantic, North Atlantic, into the high northern latitudes there. And even though the biggest volume transport of the Gulf Stream is due to that horizontal wind-driven gyre, by far the biggest heat transport is due to the overturning circulation, because the heat transport, of course, is the volume transport times the temperature difference between the northward warm branch and the southward deep branch. It's that temperature difference which makes for a big net heat transport. And the temperature difference between the western and eastern part of that horizontal gyre is quite small. And that's why the gyre circulation, the wind-driven circulation, is not the major part of the heat transport, even though it is a major part of the Gulf Stream volume transport. So that's that kind of as an introduction to what this circulation actually is. It's been in the headlines recently. This is an article from the New York Times from the 2nd of March, because of a slowdown in the Atlantic overturning circulation. And of course, that's just a newspaper article. And so with newspaper articles, it's always important to ask how accurate is it? And for that, we have a fantastic initiative which is called climatefeedback.org, which was founded by a young postdoc. It just shows that as a single person with a good idea, you can actually really achieve something. And the goal is to check the accuracy of media articles on climate change. And the method how that's done is that the team of climatefeedback.org looks for experts in the relevant field, and that's real scientists really working on this topic, as you can find out from their peer-reviewed publication record. And then it gets a bunch of these experts, maybe 5 or typically 4 or 5 or 6, to comment on the accuracy of media articles. And then there is a detailed, there are detailed annotations and a summary on the website, and also a kind of school mark here. And these scientists who reviewed that New York Times article, they gave it between high and very high scientific credibility. So apart from some minor issues, that was a good media article. That is often not the case, because they also check items from the Daily Mail or Breitbart or so, where it's often just total nonsense what is written there. But they also check good articles. So this just as a little recommendation, climatefeedback.org is an outfit worth following. Just a little bit of history before I come to this topic of the weakening of the Atlantic overturning. The first map of the Gulf Stream dates from Benjamin Franklin, 1769. You can see it on the left here. And the fact that there is this kind of overturning circulation was actually first discovered by a slave trading ship, where a British clergyman had given the captain a device which he could lower into the depth of the ocean on a rope, and that would kind of close off and capture water from the depth. And they pulled up on this slave trading ship when crossing the Atlantic, they pulled up water from the depth in the tropics and found it was very, very cold. And they mainly found that great because they could cool their wine with it. But it was a discovery of the fact that the deep ocean is cold, and that in the long run, that can only be maintained by an overturning circulation, because if the ocean wasn't moving, if it was just like a bathtub and it's heated from above, from the sun, the heat would diffuse down and eventually heat the whole water column. But the fact that the deep ocean is cold is because the deep water is continually renewed with cold water from the northern high latitudes and also from the Southern Ocean, where we have this deep sinking motion, which drives this overturning circulation. Now, this picture of the Gulf Stream is rather simplified when you compare it to a modern visualization. Here's a nice one from NASA, based on a high-resolution model of the ocean. And what you can see here is quite similar from what you can see on satellite images. The ocean, of course, doesn't flow like one straight river. It is a highly complex, turbulent, meandering fluid. And those schematic diagrams of this conveyor belt-like flow that you often see, and as I had in my introductory slide, they are strong simplifications of a much more complex reality. Here is another depiction that is also still quite simplified. You can see that there's no meanders here in the Gulf Stream. It's still shown as a straight line. It just shows a bit more complexity in the high latitudes there around Greenland and Iceland with the overflows, the northward flow into the Nordic seas, and then there's deep overflows from the Norwegian Greenland Sea back into the northern subpolar Atlantic. This whole system is, by the way, part of a much larger global overturning system, which is depicted here in a very simplified schematic way. And you can see that in the other northern ocean basins, there is no sinking. These yellow dots here, they indicate the sinking of deep waters, the so-called deep water formation process, which drives this overturning, and it simply doesn't happen in the North Pacific, for example, nor does it happen in the North Indian Ocean. This only happens here in the high latitude North Atlantic, and that makes the North Atlantic so special, and it makes it warmer than other parts of the ocean at the same latitude, because that warm surface flows towards those sinking regions where the water then vanishes down into the abyss. In Earth history, this ocean circulation, especially in the Atlantic, has been quite unstable and repeatedly flip-flopped between different states. That is pretty well documented by now. And the early evidence for that came from the Greenland ice cores. The blue curve here is from Greenland ice core and shows the second half of the last ice age, from 60,000 before present to 10,000 years before present. After that, everything is quite stable here. The last 10,000 years, the Holocene, have a stable circulation at that upper level here. But before then, in the ice age, we had these sudden events. They are numbered here, 1, 2, 3, 4, 5, etc. They are called Dansgaard-Oeschger events, and they come with a change in ocean circulation that is shown by the green curve, which comes from sediments from the subtropical Atlantic. And you can see that there's a very close correspondence in these abrupt events in the sediments, which indicate ocean circulation changes, and in the temperatures in Greenland, shown by the blue curve. And there's actually, in the meantime, there's lots of different evidence showing that these abrupt Greenland events were linked to ocean circulation changes. These red boxes here, they indicate Heinrich events, and these are events where the Atlantic overturning circulation broke down altogether for a time, hundreds of years, maybe 1,000 years. They don't show up very clearly in the Greenland ice core record because, well, for reasons I can probably best explain in the next slide. In the last ice age, we had an overturning, highly simplified, again, even more simplified, that looks a bit like this on the left-hand side. And the point is that the sinking happened well south of Iceland there. This line, this is the sea ice cover during the last ice age. So the whole Nordic seas were covered by sea ice. You can see continental ice as well on North America and Scandinavia here, the Fennoscandian ice sheet. And so if this overturning version during the ice age didn't bring the heat all the way up to the latitude of Iceland and Greenland. And so the Greenland ice core was taken on the summit here in the middle. And so when this breaks down, this would have little effect on the Greenland temperature. And that's why the Heinrich events, they don't show up clearly in the Greenland temperature. They show up if you look at temperatures from sediment cores off the coast of Portugal, for example. But the abrupt warming events with the numbers, these are the Dansgaard-Oeschger or DO events, we believe occurred when this deep water formation connected to deep convection happened in the Nordic seas episodically. And so this conveyor belt pushed north past Iceland into the Nordic seas. And then it brings the heat far up north enough to actually warm Greenland. And that's why these Dansgaard-Oeschger events, they show up in the Greenland ice cores. So what we learn from the past is that this Atlantic overturning circulation has a tendency to do flip-flops. It is potentially unstable. can actually change quite rapidly. These Dansgaard-Oeschger events, these sudden warmings happened in the time span of about 10 years, and warming of the order of magnitude of 10 degrees, more than actually shown in this very coarse resolution model simulation. What this is based on, these temperature contours. The data from Greenland show a stronger warming and a very, very rapid warming. So we have a potentially unstable circulation here, and we are in a rapidly changing climate. This is the temperatures of the last 2,000 years. The scale is somehow got lost here. Sorry about that. It has cut off a little bit of the graph, but it's the last 2,000 years, beginning from year one, the birth of Christ, from the Pages 2K project. It's a big international paleoclimate research project, and 2K stands for last 2,000 years. Plus 20 since the turn of the century, and you can see that we are undergoing a very dramatic warming that is unprecedented, not only in the last 2,000 years, but there are other proxy data from sediments going back way into the last ice age, and they show that current temperatures are very likely higher than any time in the entire Holocene, and therefore the entire history of Homo sapiens. Now, this climate change affects the ocean. One thing is that 93% of the heat trapped, the additional heat trapped by greenhouse gases and stored on Earth, has been stored in the oceans. This is not because the oceans have warmed more than the atmosphere. It is simply because the oceans have a larger heat capacity. The surface ocean has warmed practically as much as the atmosphere, a little bit less because land surfaces have warmed faster than the ocean surface because of that large heat capacity, which means there is a thermal inertia in the system. The ocean warming is lagging behind the land surface warming. But 93% of the heat trapped goes into the oceans, and it causes this steady linear increase in ocean heat content. And there's actually, in the increase in ocean heat content, there's less variability than in the global mean surface temperature because of that inertia effect. The upper ocean is a large heat reservoir. So how does that affect the overturning circulation? That is the big question. If you look at the IPCC projections, this is from the fourth assessment report from 2007, a typical global warming projection for the end of the century, for the year 2100, for quite a strong warming scenario. You see that there is warming everywhere on the planet. You have particularly strong warming up in the Arctic here, because of effect called Arctic amplification. But you have a minimum of warming in the subpolar North Atlantic, south of Greenland and Iceland here. And that minimum of warming, there's very little warming here. It's less than half a degree in the center of that blob here, has been predicted. This is an average of all the climate models that have contributed to that IPCC report. So on average, the climate models predict that. And in the models, we know the reason for that. The reason is a slowdown of the Atlantic overturning circulation, which transports its heat just into that region here that has warmed very little and gives it off to the atmosphere. And so if the Atlantic overturning circulation slows down, it brings less heat into that area, and that reduced heating by ocean circulation to some extent counteracts the heating by the greenhouse gases. Now that's a model prediction. What is actually happening in the real world? Now this is the temperature anomaly the graph by NASA. Sorry, it's in Fahrenheit. This is because it's from the US. But it does show the temperature anomaly relative to the baseline 1950 to 1980 that NASA uses. In those 5 years that are indicated here, 2014 to 2018, and you can see that everything looks pretty orange-red except for the subpolar North Atlantic, which had a real cold anomaly in those years, which has been dubbed the cold blob. Now that doesn't only happen in those 5 years, but rather this actually also shows up as a trend since the beginning of the 20th century. So this is the linear trend of temperature, surface temperature, since the early 20th century. And you can see the entire globe has warmed with one exception. It's the subpolar North Atlantic, which has actually cooled in that time interval. And so the observational data show a cooling here, which is what I believe indicative of a slowdown of the Atlantic overturning circulation, and which is totally unique on the planet. Nothing else has cooled. Now, of course, there were the question marks. There was a bit of a discussion when we published this in 2015, and some people argued this cooling could be due to aerosol pollution, although it's unclear why it should just gather over the subpolar North Atlantic, this aerosol pollution, which would shade the sun if it does that. And so we looked into this a bit more deeply, and especially my PhD student, Levke Cesar, published this paper in Nature 2018, where we compared the global climate model, which we think has the best Atlantic Ocean circulation because it has an extremely high resolution of the ocean. And this picture shows the changes in sea surface temperature in a CO2 increased run relative to the global average change in sea surface temperature. And so everything that is blue has warmed less than average or even cooled. In fact, a lot of that area has cooled. And everything that is orange or reddish has actually warmed more than the global average. And if you look at it in that way, you see a very clear dipole pattern here. In fact, if you count this special warms of Scandinavia, it's a kind of tripole. So there's more to it than just this cold blob. And we know that these other features also have to do with changes in ocean circulation, with a weakening overturning circulation here, especially that warm part of the North American coast is linked to a weakening overturning. The theory behind that is understood, has been published quite a few years ago. It has to do with the Gulf Stream shifting closer inshore when the overturning weakens, has to do with vorticity conservation. That's something for the oceanography students. This warming here probably is due to a stronger transport of heat also out of that cold blob into the Nordic seas. So that's the model simulation. Now, Levke actually compiled all the available sea surface temperature data sets and looked at the observed trend again since the beginning of the 20th century, and and plotted in the same way as that right-hand side diagram. It looks like this, and you can see this very marked structure in the Northern Atlantic again, which is very similar to what you can see here in the simulation. And the only difference is that it is kind of fuzzy because we don't have so many data in the model. Of course, we have all the information, and here we only have information when measurements were taken out there in the ocean, which is obviously not a complete coverage. That's why it's a bit out of focus. But I would argue it is a very particular fingerprint pattern, especially with this extra warming here of the North American coast attached to that cold blob, which is very clearly seen here in the climate model. And in the climate model, we know it's due to a slowdown of the Atlantic overturning, and the theory of that is understood. And so we think this is a very strong fingerprint that shows us this cold blob, this whole phenomenon here indicates a slowdown of the Atlantic overturning. There are additional studies with different pieces of evidence. I could show several here, but in the interest of time, I just show this recent paper by Christopher Pikach from, I think, Woods Hole Oceanographic Institution, who showed that the Florida current, which is kind of the southernmost part of the Gulf Stream that comes here out of the Gulf of Mexico and goes around Florida and then up north where it joins the Gulf Stream proper, that has actually weakened. And he was able to reconstruct that from sea level differences between the Florida coast and some of the islands, because again, something for the oceanography students, because of the geostrophic balance between the pressure gradient and the Coriolis force, when you weaken this current, the sea level comes up on the left side, on the inshore side of the Gulf Stream. And that's because our long-term sea level observations there, he was able to establish a long-term weakening of the Florida current, which was, he did a heat budget calculation. This weakening was just enough to explain that cold blob here in the high latitude Atlantic. So it's another consistent piece of information. And quite recently, in February, we published this paper in Nature Geoscience, again, led by my former PhD student, in the meantime, Levke Cesar. She's now at Maynooth University in Ireland. And there we compiled a whole number of proxy data series, mainly from sediments. You can see all these dots here in the inset map around the Northern Atlantic. That's the locations where these data come from. And they have been published individually in individual proxy data peer-reviewed publications. And what we did is compile them here. And the longest series goes back 1,600 years. Overall, there are 11 different data sets with different methods, different locations, but all indicative of the strength of the Atlantic overturning. And although they differ in the details, they actually show a highly consistent picture, pretty stable circulation for well over 1,000 years, and then a decline into the 20th century, which really took off in the mid 20th century. If you look at the close-up on the right-hand side here, it's a shorter time period, just since 1880. You can see after about the mid 20th century, after about 1950, things start to go down significantly. And so we think this is pretty strong evidence now. We have different methodologies, different locations, different research groups, all finding consistently a weakening of the AMOC. AMOC, by the way, stands for Atlantic Meridional Overturning Circulation. So a few words about the causes of that weakening. And a key reason is that with global warming, fresh water is added to the Northern Atlantic, and fresh water is less dense than salt water. It is lighter than salt water, so it's less heavy, so it doesn't sink so well. And so if you dilute the salty ocean waters with fresh water, you basically inhibit the sinking, that deep water formation process. And the fresh water has numerous sources. The first one is an increase in precipitation into the high latitudes, which is a fact because the water cycle gets enhanced in a warmer climate. There is more evaporation in the subtropics and more rain falling in the high latitudes. And A second effect will be the melting of sea ice, which is of course declining quite strongly, and that releases fresh water, which gets transported out here into the subpolar North Atlantic. And then we have Greenland, a huge continental ice sheet sitting right here in the middle of next to these deep water formation regions. And there is, of course, also an ongoing and accelerating melting of the Greenland continental ice sheet. All that contributes to reducing the salt content of the surface waters in the subpolar Atlantic. This is an observed trend. And we believe it is the reason for the weakening of the Atlantic overturning circulation. It's a well-established thing. I started doing such model experiments in the early 1990s, adding fresh water to the Northern Atlantic to see how the Atlantic overturning then weakens. Now, there are already some consequences of the weakening. One of them is a little bit counterintuitive, especially if you have watched the Hollywood movie The Day After Tomorrow, where the Atlantic overturning breaks down abruptly and plunges the Earth into an ice age. That's, of course, Hollywood fiction. And interestingly, I had a discussion with Jeffrey Nachmanoff, the screenwriter of that movie. I actually was also in a talk show with Roland Emmerich on German television, Emmerich being the director. But Jeffrey Nachmanoff interestingly told me that if they had been in the business of making films for a few million viewers, they would have stuck to the laws of physics. But because their business is making films for a few 100 million viewers, they stick to the laws of Hollywood drama. And that's why they accelerated everything fantastically and exaggerated. And they even had a tsunami going into Manhattan, which is nothing conceivably to do with the Atlantic overturning circulation. Anyway, so if you have seen this movie, you think it's going to get really cold when the overturning slows down. And that, of course, is true out in the Atlantic, where we have this cold blob, but it is not true in Europe. There is a study by Aurélie Duchesse and colleagues from 2016 that shows quite the contrary. When it is cold out in the Atlantic here, this correlates with increased summer heat in Europe. And the reason is this kind of air pressure effect. This cold blob tends to attract a low pressure area above it. Possibly interesting for the weather in Iceland as well, I would say. And the jet stream likes to go around the southern end of that low pressure area because there's counterclockwise movement around low pressure. And so what does this mean for Europe? The air that is coming into Europe goes to the south here where it's warm and heats up, and then it comes from the southwest into Europe and leads to heat waves. And the record-breaking heat wave 2003 in Europe was one case in point in this study. It was particularly cold out in 2003 in the subpolar North Atlantic, and that European heat wave of 2003 led to 70,000 fatalities, especially in France. That heat mortality spike is still higher than any other mortality spike in France, including the COVID-19 pandemic. The total number of deaths is larger, though, in the COVID-19 pandemic because it lasted longer than that heat wave. Another effect that has been studied is that a weakening of the Atlantic overturning leads to stronger winter storms in Europe, studied by Jackson and colleagues. And this is kind of in this red band is where you get increased winter storminess. And so this is something that affects especially the people in Britain, but also here the German North Sea coast and Danish North Sea coast. There are further effects that I won't discuss in any detail. One of them is sea level hotspot on the American coastline. It has to do with that rotational effect, the vorticity conservation. When the current slows down, the sea level on its left-hand side comes up. and this is on the North American coast. So that's additional sea level rise in addition to the global average sea level rise, simply by changing the slope of the ocean surface. Then there are likely big impacts on marine, sorry about the typo here, this E goes, marine ecosystems and fisheries. This Atlantic overturning circulation is a key reason why the North Atlantic is a particularly productive, fertile region, supporting very strong fisheries. And there's a real concern that this is going to decline when the overturning circulation gets even weaker. Another point is the reduced carbon dioxide uptake by the ocean, because obviously about 30% of our CO2 emissions are going into the upper oceans. We pump the CO2 into the atmosphere, but because the concentration rises there's a concentration difference at the sea surface, and there's a net uptake of CO2 by the ocean surface. And of course, the ocean can also take up a very limited amount in its surface mixed layer. But if you transport CO2 into the deep ocean, there's a huge reservoir there where you can put lots of CO2. But by slowing down the deep water formation process, we are reducing the amount of CO2 that is brought down into the deep ocean, and that could potentially enhance global warming. Now, there is a further point that I want to spend a little bit of time on, and that is the question of tipping points in the climate system. Here's a kind of update on what we know about tipping points that we published in Nature in 2019. And here's a map of various tipping points in the climate system. Now, tipping points are parts of the climate system, or rather, that's the tipping elements are the parts of the climate system, which can cross a critical point, and that then is a tipping point, a critical point where the further evolution becomes self-sustained. It's like a vicious circle and continues to roll even without further drivers, without further warming, without further CO2 emissions. And classic examples are the ice sheets, the Greenland ice sheet, the West Antarctic ice sheet. If they melt, their surface, that's especially true for Greenland, this mechanism. If it melts, the surface gets lower down in the atmosphere and therefore into warmer air, which enhances the surface melting. So it's a self-sustaining positive feedback. And that gets triggered at a certain critical point, which is somewhere between 1 and 3 degree warming thereabouts. We could already be crossing it now, basically. For Greenland, there's some discussion about that. And that means once we pass that point, we don't need any further warming. The Greenland ice sheet will get lost altogether, causing 7 meters of global sea level rise. Luckily, that takes a while, hundreds of years, but once that critical point is crossed, it basically becomes a self-sustaining process. And these, there are various tipping points. I won't go through all of them, but you can see there are some connections between these tipping points. Greenland ice sheet melting could trigger the next tipping point in the Atlantic circulation. Also, the Arctic sea ice melting, that first of all can trigger the Greenland ice sheet tipping point because the whole region gets warmer, and therefore that helps the ice melt. If the sea ice goes, it helps the continental ice sheet to melt. And secondly, that meltwater also dilutes the North Atlantic, affecting the Atlantic overturning circulation. And so these tipping points, they hang together. And that's where this quote from the article comes in. The clearest emergency would be if we were approaching a global cascade of tipping points. They can trigger each other like dominoes. But let me explain what this Atlantic overturning circulation tipping point is. This has been established basically since the work of Henry Stommel in the 1950s, who used a very simplified model with just 2 ocean boxes to show that the deep water formation process in the Northern Atlantic is a self-sustaining process governed by a positive feedback, which is very simple. This northward flow doesn't only bring heat into the high latitude ocean, it also brings salt into the high latitude North Atlantic. Remember, I told you that these high latitudes are a region of net precipitation going into the ocean, and that would dilute the surface waters. But it's balanced by the fact that continually the Gulf Stream and North Atlantic current are bringing more salty water from the subtropics, which tends to increase the salt content of the subpolar Atlantic waters, makes them denser and helps them to sink. So the water sinks there because it is salty, and it is salty because of that sinking and the water that it draws into the sinking region from the south. And so that's a self-amplifying feedback, and any physicist will know this is a condition for multiple equilibrium states and tipping points. And this is what you see in this diagram here. On the bottom axis, you see the amount of fresh water being dumped into the ocean. So the further to the right, the more fresh water goes in, let's say rainfall or meltwater from Greenland. And on the vertical axis, this curve shows the strength of that overturning, the Atlantic overturning circulation. And there is this area in between here, this with a colored background, where you have 2 stable states, one at the bottom here where there is no overturning, and one with the overturning switched on. And whether you're on that upper branch or in that lower stable state depends on your initial condition. It depends where you started off. And so if we start off here, let's say the present climate is here. Nobody knows exactly where on this curve it is, but the strength is about 17 million cubic meters a second, or Sverdrups. That's why the scale here goes from 0 to 20, but it's only indicative numbers. This is a schematic diagram. We don't know the exact numbers behind this. And so if you add more fresh water by ramping up Greenland melting, we will move to the right on this diagram here until we hit this bifurcation point, and then there is no more a stable equilibrium. And then we will fall down this cliff here onto that switched off state. And so that is the tipping point, or I call it the Stommel bifurcation point, because Henry Stommel was the first to describe this. And this simple system with 2 equations, which leads to a parabola as a solution, and this parabola is what you see here. This dashed line is an unstable equilibrium where any tiny perturbation will make it move away from that. And so if you start a little bit above the dashed line, you will fall onto that upper branch. If you start on that below that dashed line, you'll fall onto the lower branch. So the dashed line separates the basins of attraction of these 2 equilibrium states. So this has been established now with 3-dimensional global general circulation ocean models. So it is something that is pretty well established, that this bifurcation structure that we see here with that tipping point actually exists. What we don't know is how far away from that tipping point are we. Now that's a shame, because it is a real high impact event should we pass that tipping point. That would greatly upset the machinery of our entire planet. Of course, especially the North Atlantic, we have seen that in the history of climate, in these abrupt glacial events, that this has a massive impact on temperatures in the North Atlantic. Here is a recent model simulation by some colleagues working in America and China, showing the temperature change if you collapse the Atlantic overturning circulation as part of a global warming scenario. And so all around here, you get warming because of global warming, increased CO2. But in the Northern Atlantic region, you get this a strong cooling. And sorry, folks in Iceland, you don't really like that. Yeah, this is like getting 9 degrees centigrade colder there. It's already pretty cold in Iceland. One of the times I was giving a talk in Iceland and Haldor Björnsson from the Iceland Met Service, I hope Haldor doesn't mind me telling this anecdote, he gave the introduction and he said, Icelandic people are all climate deniers. They live in constant denial that the climate is actually too cold to live there. And so I don't think you want it much colder, as would happen if we collapsed the overturning, but also Britain, Scandinavia would be massively impacted. But it's not only these local impacts on the North Atlantic region that make potential passing of that Atlantic circulation tipping point so extremely dangerous. It's also far-field effects like a shift in the tropical rainfall belts, which will happen because the whole northern hemisphere will then cool relative to the southern hemisphere, and the tropical rainfall belts are on the so-called thermal equator where it's warmest, and presently that's north of the geographic equator, because due to that overturning, the northern hemisphere is warmer than the southern hemisphere. But if you collapse it, the thermal equator will shift south, so will the tropical rainfall belts, and sediment data from these Heinrich events show that this has happened time and again during the last glacial period. So there are a lot of very serious effects that, in my mind, mean that we have to prevent a collapse of the Atlantic overturning at all costs, basically. The problem is we don't know where that tipping point is. It's like navigating in a fog into waters with treacherous rocks under the sea surface, and you don't know where they are, but you know there is a real risk. And so that really calls for the application of the precautionary principle. That brings me to my final words on what can we do, what should we do. In view of all these risks of climate change, in 2015, the Paris Accord was unanimously agreed by all the nations on the planet. Practically everyone has ratified that. The United States, thankfully, are back in since the new Biden administration has taken office. And the Paris Agreement aims at holding the increase in the global average temperature to well below 2 degrees above pre-industrial levels. And don't forget this, to pursue efforts to limit the temperature increase to 1.5 degrees centigrade. That is very important. With the 2 degrees, it's also very important to not forget the well below 2 degrees. The United Nations Framework Convention on Climate Change had already years before agreed to a 2-degree limit, but in Paris, this was strengthened to a well below 2-degree limit. And without that strengthening to well below, many nations would not have signed on to the Paris Accord. And that, unfortunately, in the media often gets forgotten, as if limiting warming to 2 degrees would be Paris compatible. And certainly, the nations have committed to pursue these efforts to limit the temperature increase to 1.5 degrees. And because there is a real danger that we pass the critical tipping point for the loss of the Greenland ice sheet somewhere between 1.5 and 2, we probably commit the world to the loss of all coral reefs between 1.5 and 2 degrees. And we start even to run a risk of triggering further tipping points like the Atlantic overturning tipping point. These are all very good reasons to absolutely implement the Paris Agreement. My final slide, what does that actually mean? It does mean we have to reduce emissions like the solid lines for 50% chance to stay below 1.5 degrees. And had we started in 2016, after the Paris Accord was made, we could have reached zero somewhat before 2050. Now we're later. Here I assumed after the COVID dip, we go back to 2019 levels this year. And then we have to go down, already reach zero near 2040. And if we wait another 5 years or so, then within 10 years we have to go down to zero. That's obviously impossible. So at the moment we are losing the chance to really limit warming to 1.5 degrees. We have to act very fast from next year. Emissions have to drop, otherwise we simply won't make it. So thank you very much for your attention. If you want to read more, here's some suggestions. Follow me on Twitter. And I stop right there because I want to have some time for your questions.